We now turn to considering various approaches for solving the travel and salesman problem. As usual, we start with probably the most naive possible approach. Okay, so namely, we're going to consider an approach that just enumerates all possible candidate solutions and among all of them selects the best one. This is known as a brute force search or a brute force approach. So first of all, let's try to understand what is our set of all candidate solutions. So what I claim is that what we're looking for is more or less a permutation of our n given nodes. So why am I saying more or less? Well, let's see. Assume that we have just four nodes. Indeed, what we need to, so I'm drawing only the nodes of our graph, but at the same time we have all possible edges between them, and assume that our graph is directed, for example. So what we need to find is actually an order of visiting these nodes. For one such order is, for example, BDCA. This corresponds to the following. So this is a permutation, right? And of course it defines a cycle. So from B we go to D, from D we go to C, from C we go to A, and then we return back to B, I'm sorry, because this is the first element of our permutation. At the same time, this correspondence is not one-to-one. Namely, in our permutation there is a first element, of course, B, while in a cycle there is no first element, right? So this actually means that for one cycle there are n different permutations, where n is the number of nodes. Namely, there are n different permutations which give the same cycle. So, for example, the permutation DCAB also gives rise to the cycle shown here on the slide, and also CABD, and of course ABDC. So they all give the same cycle because they basically correspond to the, for example, DCAB is like a cycle, is the same cycle where we start from the vertex D, from the node D. Okay? So, but still, roughly, when we're looking for a cycle, we're looking for a permutation. Okay? Or for a permutation with some first node fixed. This basically tells us that the number of different cycles is n minus 1 factorial. So n factorial is the number of all permutations of n objects, but because we can assume that the first node is fixed, right? So if the first node is fixed, then for the second node there are n minus 1 choices, for the next one there are n minus 2 choices, for the next one there are n minus 3 choices, and so on. So the total number of cycles, of different cycles, is n minus 1 factorial, which is almost the same as n factorial. Okay? And unfortunately, the n factorial function grows extremely fast. Okay? So just to show you how it looks like, note that, for example, n factorial when n is equal to 5 is equal to roughly 100. So this is, let me just remind you, this is just 2 times 3, which is 6 times 4, which is 24, and times 5, which finally gives you 120. Okay, this is a reasonable number. I mean, we can definitely implement a program that goes through 100 possible solutions and does this very quickly. However, when n grows, n factorials gets longer and longer and longer. For example, already when n is equal to 20, 20 factorial looks like this, so definitely more than 10 decimal digits. And when n is equal to 30, n factorial is a huge number. So definitely our modern laptops are not able to perform so many operations per second, not even per second. I'm not saying, and even not in an hour, or even not in 1 year. So an algorithm working for n factorial operations is not going to be practical even for n equal to 30, unfortunately. So this also tells us that the search space in case of the travel and salesman problem is huge. It is impossible to explore the whole search space to find the best solution. Okay, so, and this tells us that we definitely need some smarter approaches. But before going into such approaches, let's explore also the following idea. We've just realized that it is not affordable kind of to go through all possible permutations. But what about just selecting the random permutation? Let's just pick a random permutation out of all possible permutations and hope that it is going to give a not so long cycle. So unfortunately, it turns out that the length of a random permutation may be much worse than the length of the best permutation, even if we consider a special case of Euclidean TSP. So as I mentioned already, in case of Euclidean TSP, sometimes solving such instances is easier, in particular because they satisfy this triangle inequality. Okay, and it is not actually too difficult to understand why it can be that bad, but it can also be shown formally. So the lemma that you see here on the slide actually tells us that tells us how to compute the weight of the a random permutation. And when I say the weight, I mean, of course, the expected weight. Okay, so the expected weight of a random permutation is equal just to the sum of the weights of all edges divided by n-1. And here I assume that we have a directed graph. Okay, so informally this can be proved as follows. So in a cycle we have something like we have exactly n edges, and in a complete directed graph we have n times n-1 edges. And since everything is symmetric, each edge has probability 1 over n-1 to be included into a random cycle. Okay, and then which means that for each edge, its contribution to the expected length is its weight divided by n-1. Okay, so in this, since the expectation is linear, we can compute the total weight as the sum of expectations of all the edges, which gives us the sum of all edges divided by n-1. If you would like a more formal proof, you can argue as follows: the total number of different cycles, as we've discussed, is n factorial, right? Is n-1 factorial. I'm sorry. Now let's do the following. Let's fix a particular edge, for example UV, and let's count the number of cycles that contain this particular edge. Okay? Since, as you remember, since we have a cycle, we are free to select its starting point. So let's just assume that so we have a cycle and we are counting the number of edges, the number of cycles that contain the edge, UV. So let's assume that U is the starting point of this cycle. And since it has vertex V here, we know that there is U and V here. And for all the remaining edges, for all the remaining nodes, we are free to select any particular permutation. So any of n-2 nodes here, any of n-3 nodes here, and so on. So the total number of permutations that contain this particular, the total number of cycles, that contain this particular edge is n-2 factorial. So the fraction of all cycles containing a particular edge is actually 1 over n-1, and this is also a probability of a fixed edge to be included into a random cycle. Okay, and this, let me erase now everything and let's discuss this. This means that if we now graph, we have some very heavy edge, then it will give the contribution to a random permutation also, right? Its weight will give a contribution to the weight of a random permutation, and this is something that we would like to avoid, because probably there are many heavy edges in our graph, but what we're looking for is some cycle that avoids all the heavy edges, right? Probably a more interesting example is the following. So consider just this simple data set. So we have some bunch of points here at the bottom left corner, and some bunch of points here at the top right corner. So of course, for this particular example, it is not so difficult to convince yourself that the best cycle looks like this, right? So we first need to somehow traverse all the nodes here at this corner, then we go to the opposite corner and traverse all the nodes here, and then we go back. Namely, so there are two groups of points in at different corners, and it makes sense, of course, to go only once from one corner to that corner and then to return back. Okay, but if you consider random permutation, then it will look like this. So it will take too many long edges, and that's exactly why a random permutation may be much worse than the optimal one. Okay, so in the next videos we are going to consider smarter approaches for solving the trial and salesman problem. In particular, we will start with an approach that can easily solve this particular data set. And you've probably guessed already, so there is a very reasonable heuristic to solve this particular one. So from each node, let's go to the nearest node which hasn't been visited yet, right? So this will solve this particular data set immediately, right? Because from starting from that node, we will go to that one, then to that one, to that one, then to that one. Then the next unvisited node is this one, I mean the closest one. This will lead us here, 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 and finally here. So in a sense, this data set is not so difficult to solve in practice. So in the next video, we are going to explore this approach further.